So we are very happy to hold those Balzan lectures to celebrate the discovery of the first binary pulsar by Russell Hulse and Joe Taylor in 1974. And we are very fortunate that Joe himself has accepted to say a few words of introduction for these lectures. Joe?
Thank you so much, Thibault, and good afternoon, everyone. It's a real pleasure to be with you, even though it would be even more pleasure if I could be there in person. Looking back 50 years is a lot of fun. It brings back some very happy memories. And for just a few minutes, I'll try to share with you some of the excitement that we felt at the time when this discovery was being made. In 1974, I was a young assistant professor at the University of Massachusetts. We had a small radio astronomy group designed, first of all, to observe pulsars. The first pulsar had been discovered just a few years before. We were among the first Americans to be involved with follow-up observations of the early pulsars and finding new ones. And I had already become very interested in trying to do more of that work. Russell Hulse, it turns out, is my very first graduate student. He was a physics student rather than not particularly astrophysics, but I talked him into taking on a project that would involve the use of a specialized laboratory computer that we would transport to the Arecibo Observatory and program in a way that would take advantage of digital techniques that were just then becoming possible for the first time. I had, anyway, ideas about detecting many more pulsars, and Russell Hulse was very happy to join me in the project. Part of the reason that we were so successful was that we realized that this was necessarily a very multidimensional search. Not only did we have to search for these objects in different directions in the sky, but we had to look for pulsations with different periods, at least over the range of periods that were then known for pulsars at the time. At that time, there were only about a few dozen pulsars known. And we thought we had a technique put together that would enable us to at least double the number of known pulsars, probably more than that. As I mentioned, it was a time, this was 1972 when we were first starting the project, when small computers were available for sufficiently small budgets that they could be used in laboratory settings. And the idea was that we would buy a cheap, what were then called mini computers, and program it to do the period search and to also allow for a wide range of different pulsar dispersion measures. Pulses propagating through interstellar space are delayed delayed at lower frequencies compared to higher frequencies because of the dispersive nature of the interstellar medium, and that had to be taken into account. The computer that we had, we were very proud of. It was a delightful machine to play with in these very early days of digital computers, but its capabilities are almost laughable today. The machine had 16,000 words of memory. Each word was 16 bits. There was no operating system. There was no compiler. We had to program everything from the ground up using machine language or assembler code. The total 16,000 words of memory meant that we could at most use about half of that for the digital signal processing required, and the rest of it for a sort of homegrown operating system that would make the computer usable. Anyway, we did these things. We transported the system to the Arecibo telescope in Puerto Rico and started observing and detecting new pulsars. The system worked well. It was efficient. It was an effective way of using the telescope. It was substantially more sensitive than any previous pulsar searching approach had been on any telescope anywhere in the world. Something like an order of magnitude more sensitivity, partly because of the large collecting area of the Arecibo telescope and partly because of the computer technique that we were using. In any case, by the summer of 1974, Russell had already found several dozen new pulsars, and one showed up one day in July 1974 with a very short period, about 59 milliseconds, shorter than any other pulsar known at the time except for one, the very young object in the Crab Nebula. And we assumed that it was fairly likely that this object would also be a young pulsar, perhaps in a supernova remnant. Anyway, we followed it up. We discovered that on subsequent days, the period was almost the same, but not quite the same. And this was puzzling at first. But we looked for all possible ways of explaining the observations away. Finally, Russell decided to follow it very carefully for as long as we could track it at the Arecibo telescope, which is about 2 hours per day. And he discovered that indeed the system was repeating the changes in apparent period in a way that could be interpreted as a Doppler shift in a binary orbit. The orbit turns out to be close to about 1/3 of a day, 8 hours. And that was part of the reason that it was difficult to work out the orbit, because we only get to observe for a couple of hours per day in the transit telescope at Arecibo. And that meant that we had only a small portion of the orbit on each day and almost the same portion on successive days. Anyway, within a few weeks, Russell had worked out what was going on. We had, in fact, a rough idea of the size and shape of the orbit, and we were astonished to discover that this object was mildly relativistic, and that relativistic gravitational effects might turn out to be important. And of course, that is why the system turned out to be so important. And I'm not going to go any further into that at the present, because in fact, you're going to be hearing about it from both the theoretical side and the observational side from the two speakers in these Balzan lectures. It took 15 years and more before really highly precise measurements were available. And those we proceeded to do religiously, more or less observing every year for a couple of weeks and improving the equipment along the time. And we're able to eventually establish that the system was losing energy at the rate expected from the emission of gravitational waves from the system. And that, of course, is much of why the system has turned out to be so important. I won't say more. It has been a great pleasure working on this for most of my professional life. It has been a great pleasure having such good friends as Thibault and Michael and others to work on it with together. The system has been important. It has among other things, shown that the very ambitious project that ended by great success in detecting gravitational wave directly on Earth was in fact a project that was worthwhile and worth pursuing, even though the risks appeared to be quite high. And that's part of the reason why the LIGO project and Virgo were able to be funded, because by that time we knew for sure that these gravitational waves actually exist and behave in the way that relativity says they should. That's all I'm going to say, folks. I'm going to sit back and listen. I'm looking forward very much to hearing the lectures by Thibault and by Michael. Thibault Damour will speak next, and he will talk about the binary pulsars and theoretical gravity. Over to you, Thibault.
So, after this nice introduction, warm introduction by Joe, let me start. Let me mention first that on the first slide, I have put some relatively recent references which are not the original papers on what will be discussed today, but this is a review of the discovery of the first binary pulsar and its implication. There is a recent, 2021 fantastic paper by Michael Kramer and collaborators on strong field gravity tests with the double binary pulsar, which is a fantastic object. You will hear a lot about this. And there is a very recent review from July 24 by Paulo Freire and Norbert Wex on gravity experiment with radio pulsars, and I've taken pictures from this review. Then let me mention that on the web, in the particle data group page, there is a review of, if you want a short review of what are the best tests for binary pulsar, which is in this, on this website. And then on the web page of Paulo Freire, there is an updated list of the best pulsars and what you can do, what are the tests of this. So, as Joe already mentioned, the discovery was done at Arecibo. So Arecibo was at the time the largest radio telescope on Earth. It's built in the crater of some structure that fell in Arecibo. And for many years, it has been a fantastic source of information, experimental information on radio waves and in particular on pulsars. It decayed a few years ago, so it's no longer now working. Apparently, the largest telescope in the Earth as a one telescope now is a dish in China, but there are new things that Michael will talk about. Now, this is Russell Hulse, more or less at the time, and Joe at the time. So what are we talking about? So this first binary pulsar is called PSR for pulsar B. It's just a way of saying which system you use. 1913+16, which record the angles on the celestial sphere of where this pulsar is located. So a pulsar, just to keep this in mind, is a neutron star, so an object with a radius extremely dense, made of essentially of neutrons, a radius of the order of 10 kilometers, which rotates, and this one rotates in 17 revolutions per second, so a period of 59 milliseconds, around a rotation axis, and it emits a beam of radio waves, actually radio noise, which is emitted at an angle, and because of this, there is a lighthouse effect, and the width of this beam varies from pulsar to pulsar, and if the Earth happens to cut, if the line of sight from the Earth, you cut the beam of this lighthouse, then you can see this pulsar. But there are many pulsars you don't see at any moment, but you see some of them that exist. And now the important new thing about this pulsar, as Joe just explained, is after a few weeks, it was understood that this object goes on essentially in lowest approximation a Keplerian orbit, a Keplerian ellipse, actually with an eccentricity roughly given by the golden number. So at the time there was a surprise that this system was very special. Even its eccentricity was square root of 5 minus 1 over 2, 0.68. And the orbital period is nearly 8 hours. And then there is a companion, okay, that you don't observe, okay? But there is a system where we see the companion, and Michael will talk about this. Now, the announcement, so it was discovered in July initially, and then it was understood in September, and then Joe went with a new equipment to Arecibo to confirm that this was in a binary orbit. So in September, and then they wrote a paper in September that they sent for publication to Astrophysical Journal in October. And in this paper, they mention already that this is a nearly ideal relativity laboratory. Why? Because a rotating neutron star, a pulsar, as will be discussed in more detail by Michael, as you can observe, each pulse emitted when the lighthouse thing rotates to a high accuracy, ultimately a few microseconds in the best cases. And it is very stable because of the high moment of inertia. Some of the pulsars are more stable than atomic clocks. So it is as if you had an atomic clock, but going in an orbit, and therefore you can time this from the Earth, and therefore you have a high accuracy knowledge about the motion in the orbit. And also it is submitted to many gravitational effects, and immediately in their discovery paper, Russell and Joe said that we will be able, they anticipate that one will measure the second order Doppler shift. I mean, the first order Doppler shift is the fact that the frequency, that the pulsar frequency is modified by the radial velocity. This is what was observed initially. But beyond this, so it's a V over C effect. Then you have V square over C square second order Doppler shift, gravitational Einstein redshift GM over C square R due to the companion being at some distance, and relativistic periastron advance that you could estimate to be of the order of 4 degrees per year. Let us notice that the relativistic periastron advance in this system is actually, if you convert 4 degrees per year, this is 40 arc seconds per day, while you remember that Mercury has 40 arc seconds per century. So it is really much easier to see relativistic effects in this system. And I was lucky to be a young postdoc, 23 years old, arriving in Princeton in the physics department precisely in September 1974. And I still remember that I learned about the discovery of this from one of the back-hall lunches at the Institute for Advanced Study, and it became clear immediately to Remo Uffini and me that this was a very interesting system and that we had to keep it in mind and work on it because this was a new relativity laboratory. There was a flurry of papers that was published by many people on astrophysics side and theoretical side. Notably, Bob Wagoner said, and we will discuss this
later, you can probably observe the back reaction of the emission of gravitational waves in this system. Doug Eardley said, not only this, but if you did not have general relativity, but let's say any scalar field, long-range scalar field, there would be dipolar radiation emitted and not only quadrupolar, and that would make a big difference in the back reaction of gravitational waves, and therefore you can test for alternative theories of gravity from this. Our paper with Remo, which for some reason, I mean, I will explain why, it's the only paper published in December 1974, before even the paper of Joe and Russell appeared, because we sent it to the compte rendu of the Academy of Sciences in Paris, and at the time this was published in 2 weeks, so in December 19. And then in this paper, we mentioned that because of spin-orbit coupling, you have this spinning, you have a gyroscope, okay? And this gyroscope is interacting with its companion. And there should be a spin-orbit effect, which means the spin axis will slowly precess, and this will tilt the cone, the beam of emission. And therefore we said, you can see this probably. You can explore this way what is the structure of the beam and then Michael will talk about this. And then we said, and maybe this thing will even disappear in a certain number of years, okay? And we will hear from Michael about this. And then there was an important first paper by Ed van den Heuvel and collaborators to understand how the system was formed. So Michael will talk more about this, but let me give you an idea. At the time, most people thought that pulsars were remnants of supernovae. Like, for instance, when you have a supernovae and then all the matter of the star collapses under its own weight and create a neutron star, by conservation of angular momentum, even if it was slowly rotating initially, you expect that the remnant, which is very small, will rotate very fast. And
And then the idea was that all the pulsars you would observe would be in this ballpark, except the very young ones, because when they are born, they go very fast, but then they lose energy and the magnetic field disappears, and therefore they should slow down. And indeed, most of these normal pulsars have periods, rotation periods of the order of 1 second, let's say, or 1/10 of a second, except the Crab pulsar somewhere, which is 33 milliseconds, okay, because it's very young. But here, Ed van den Heuvel and others understood there was a new population, that these dead pulsars must be recycled in the binary system, and they must be spun up again. Okay, we will hear more about this. And here you have the colors in red, you have double neutron stars, okay, and there is even a triple system. And in blue, you have binary systems where the companion is a white dwarf, okay, not a second neutron star, but a white dwarf. As Michael told me, the rough numbers is that there are about 4,000 pulsars discovered in the galaxy. And 10% of them, 400 of them, are double, but only 10% of these 10% are double neutron stars, okay, which are the red dots. Okay, so we will, so these are special objects. Now, the timing. So you have this lighthouse, which is emitting a beam, and then at each turn from the Earth, you can see a pulse. So if this is the time axis, and this is the radio signal, so from this sky direction, you see nothing or a very low signal, and then you have a pulse, and then you have a second pulse. Okay. The first, as you remember, when Jocelyn Bell discovered the first pulsar, they called them LGM, little green men, because getting from the sky a very regular thing, like a pulse, a pulse, a pulse, you know, every fraction of a second with very high accuracy, then they said, okay, it's a signal maybe from somebody up there. But in this case, what happens is that it's not extreme, it's not regular. The distance between two pulses changes slightly because it moves on the orbit. So when it is on the far part of the orbit, it has to cross the orbit, etc. So at the end, the problem is the following. This is a space-time diagram. You have the binary system where you have two objects going around, so helix in space-time. And we are on the Earth. The Earth is also going around the Sun, or around the center of mass of the solar system. And from the, let's say, invariant point of view, what you want is what is the map between the proper time along this world line, which would be ideally the proper time of the pulsar itself in its own reference frame, okay? If I was next to this pulsar and I neglect the loss of energy in the form of electromagnetic waves, I should see regular ticks, okay? But I have many effects, Newtonian effects, relativistic effects, and you need finally a relativistic theory of the binary motion, a relativistic theory of how this signal, the radio waves, propagates in the gravitational field in the system, in the galaxy, and in the solar system. And then you have also to take into account the motion of the Earth. Okay, so this gives what is called the timing formula, which gives, and this is what is the next thing. So the first timing formula, because the discovery was made by saying the period changes. So what you observe is that the period has a redshift which varies with orbital period. But soon it was understood that you have much higher accuracy by keeping track of the number n, okay? The number of pulsars, which is the number of turns, okay? At each turn, you emit something which goes to the Earth. And if you do this coherently, you never lose track of one period, but you have a much higher accuracy, like, you know, integrating this from this. So the timing formula, and roughly between two things, you have 59 milliseconds, 59 modulo this Doppler effect. So this thing rotates, and you want a formula which relates the observed time by an atomic clock at the observatory on the Earth, t, let's say, or t observed, to an integer number, okay? And if the pulsar itself was really rotating with a constant speed, the number n would be just proportional to the proper time. But actually, because of electromagnetic losses of the pulsar itself, you must take into account t square and t cube. So you use a formula of this type. And the first formula, which was quite useful initially by Blanford and Tucholsky, is summarized here. Is saying that the observed time is equal to the proper time on Earth, is the proper time of the pulsar related to an integer this way. And then you have some simple cosine and sine of the eccentric anomaly. You know that the solution of Kepler's motion given by Kepler of the two-body problem, you can introduce an angle which is not the angle on the orbit, but an auxiliary angle, such that the time of the solution of the Kepler problem is related to the eccentric anomaly by this, with the eccentricity E being this. And here you have cosine and sine of this, and then you have parameters. The first two parameters, alpha and beta, are linked directly to the light crossing time. You have the semi-major axis of the pulsar orbit projected by the line of sight. So this is the time it takes to cross the orbit, essentially, projected. And then this is multiplied by sine and cosine of the angle of the periastron, okay, omega. And then the most noticeable relativistic effects here is this gamma, which is, yes, gamma is the Einstein effect and the second order Doppler effect. The fact that this clock is moving in a gravitational field means you have a second order Doppler effects V over C square, and also a gravitational redshift effect, and they combine in this parameter. And then Blanford and Tucholsky said, yeah, but the periastron will also have a secular precession, so you move the periastron linearly in time, and maybe the period also will evolve very slowly in time, and you put secular effects. Okay, so now let's have some orders of magnitude in mind. So the pulsar period is 59 milliseconds. The velocity along the orbit, roughly, although it varies between 100 and 400 kilometers per second, is roughly, let's say, 300 kilometers per second. So it's 10⁻³ of the velocity of light. So each relativistic effect gives you a factor 10⁻³. Now, the first effect, as I said, is crossing the orbit. And it is already a 1/c effect, because if the velocity of light was infinite, you would cross it instantaneously. So it is the size of the orbit divided by c, this parameter. And later we called it Römer, because Römer actually discovered, and was the first one to measure the velocity of light by using, here in Paris, the data of Cassini, who was also in Paris at the time, about the satellites of Jupiter. And then depending whether the satellite was here or there on the orbit, there was a difference in the time of observables on Earth, okay? And this way, Römer computed the value of the velocity of light in 17 something, which was already something like 400,000 kilometers per second, you know, close to the actual number. So Römer effect, so this is, let's say, 1/c, roughly speaking, and this effect on the time observable time on Earth is of the order of 1 second, okay, 2.34 seconds, okay. So compared to something which would be regular, you have shifts, varying shifts of 2 seconds, which is a lot. You measure this easily. Now, the first relativistic effect, the Einstein effect, is a 1/c squared thing, but compared to 1/c, it means you have a factor V over C compared to X, so it's 10⁻³ of 1 second, which is a millisecond. But a millisecond is also actually easy to see, because you have accuracy in good pulsars of the order of a few 10 microseconds or something like this. But the next effect is the Shapiro delay. Shapiro means you have the propagation. It's the time delay because you propagate in a curved space-time, and you are influenced. The velocity of light in GR is not c everywhere, let's say, but modified by g mu nu. And this effect gives a logarithmic term, which scales like g times the mass of the companion over c cube. So it is one, which has the dimension of time, by the way. If you take a mass, you multiply by g, you divide by c cube, it is a time, okay? And this time is of the order of a microsecond. It's v squared over c squared, 10 minus 6 of the main time, so you get something of the order of a microsecond, which is now more difficult to get. But in some cases, and we'll hear about that from Michael, especially when the inclination angle is nearly edge-on, this effect is quite large, and you can measure it with high accuracy, and you get a lot of information. And then from Newtonian physics, the orbital period of a binary system is a power minus 3/2 of the binding energy of the system, the kinetic energy and the potential energy, with power minus 3/2. And therefore, if for some reason the binary system is losing energy, then the period should change. Actually, if you lose energy, the period should shorten. The system should go faster, okay? Now, what are the losses of energy in the system? If the system was embedded in a noisy environment with gas and things like that, like a satellite around the Earth, it would lose energy from friction. But the beautiful things about this system is that it was understood little by little that they are extremely clean, and therefore it's an opportunity that it is a very subtle effect of the loss of energy in the form of gravitational waves, okay? And we'll hear also from Michael that even the tiny effect of because this is linked to the orbital motion, that the loss of energy in the form of electromagnetic waves, which means that the mass of each pulsar diminishes, has also an effect, but a secondary effect. Anyway, if you take a textbook, we are going to discuss that, but just to have orders of magnitude. From GR, it had been expected for a long time that the loss of energy in the form of gravitational waves from a binary system contains the 5th power of 1/c, where, by the way, the number 5 in 1/c5 means 2s plus 1, where s is the spin of the field. The spin of gravity is 2, so 2s plus 1 is 5. This is why we have v5 over c5 with v over c of 10 minus 3. You should get 10 minus 15. Actually, it is amplified by the eccentricity. And this thing, a dimensionless number, it's a derivative of a time with respect to a time. So it's a dimensionless number, is of the order of 10 minus 12 for the binary pulsar. But if you had a scalar field, a massless scalar field, you would emit now with spin equal 1, 2s plus 1 become 3, and then you would have v over c cube, which means 1,000,000 times larger than the GR effect. That's why you see immediately that these are excellent tests for gravitational wave aspects. Okay, now let's indeed discuss the story, because the idea, Michael will talk more about what you observed, but I want to talk about the theoretical side. Now, the 3rd edition of Landau-Lifshitz, the Bible of theoretical physics at the time, and it is the edition I had read in the French version in 1968 or something like that. In it, it contains a discussion of gravitational waves with a derivation of the so-called Einstein quadrupole formula. So Einstein quadrupole formula says that at the end, the energy lost by any system of moving masses, and Landau-Lifshitz improved the derivation of Einstein by saying, but you must take into account also some self-gravity effects. But anyway, they said the loss of energy is proportional to the square of the 3rd derivative of the quadrupole of the system, the mass quadrupole of this system. So this is this quadrupole thing. But then in this edition, and this is what I had read myself as a student, they insist in saying it is necessary to note that the numerical value of this energy loss, even for astronomical objects, is so small that its effect on the motion, even over cosmic time intervals, is completely negligible. And they cite double stars, but they meant double stars, you know, with long periods. it is so small that you can forget. And I was under this impression when I arrived in Princeton, okay? I had not realized that a small effect, 10 minus 12, actually can be seen, as we will see later. And in Landau Lifshitz, they have an exercise, it's below this page, and where they compute the energy loss for the case of a circular orbit. And I'm saying, and in it, they compute, they say, let's assume that if you lose energy, who is paying this loss in the form of waves at infinity? It's the binary system itself, and therefore the binding energy of the system should decrease, and therefore the radius of the binary orbit, the distance between the two objects should decrease, and they compute it. R dot equal this, and you can see on this thing that it is proportional to the cubic power of G, Newton's constant, and the 1 over C5, okay? So radiation reaction should be at order G cube over C5, and that will be important in the following. So what was known at the time about radiation reaction of binary system? What I'm just said is saying, at the time, Einstein and Landau Lifshitz were assuming that there should be a balance of energy between the loss of energy at infinity and the energy of the system, okay? But actually, Eddington in 1924 was the first one to saying, but actually, you should compute the radiation reaction. It should be some forces within the system that cause it to lose energy, so let's compute that. And he showed explicitly that all the existing knowledge about local field in the system was unable to reproduce the loss of energy because it was too high order effects. You need to go to G cube, third order in nonlinearity over C5. And explicitly, Eddington said, but even Laplace, you know, the first guy who said there will be an effect of the fact that gravity propagates at a finite velocity, it was Laplace in France, because Newton had posited that gravity was instantaneous, okay? That the force between this object and another object was just linked to the position of the object at the same time t. But as we know, Newton explicitly wrote, evidently any natural philosopher, which means physicist at the time, cannot believe that there is something instantaneous propagating in space. It has to propagate in some medium, okay? And Laplace was the first one of saying, okay, if the gravitational force propagates with some velocity, cg, the velocity of gravity, it should have effects on the binary dynamics. And actually, Laplace said, if it is a retarded effect, okay, if the thing propagates like that, the force acting on one body should be Newton's force, as if it were instantaneous, minus the effect of the angle, the fact that it's attracted not by the position of the object now, but a little bit before, okay? Actually, it was more subtle than this, but anyway, he said that there should be a tangential component of the force minus V over C something, which means of the damping type, you know, friction type. And then he said, let's assume that in the solar system, the moon, for instance, has a force of this type. And he said, no, it will mess up all what we know about the moon. And then Laplace gave a limit saying the velocity of gravity. I'm saying this because it was well known at the time. Let me push this. That the velocity of propagation of gravity must be larger than 7 million times the velocity of light, okay? From solar system data known by Laplace. And for a long time, people said, okay, gravity does not propagate at the velocity of light and things like that. But now, seen from the modern perspective, what we want is, if we want really to connect the theory of GR with the observations, you want to be able to compute the force acting on one body exerted by its companion, not only to first order in G, like one graviton exchange, not only to second order in G, which means diagrams where you have the nonlinear effects within gravity. This is saying that the gravitational field creates a mass between the two systems, which itself creates a force, but even at two loop, the post-linear thing. And we will, so the discovery of the binary pulsar have pushed the theorists to push the theory of the equations of motion of binary system. And between actually 1974 and 1978, there was a big debate among theorists. What is known finally about the equations of motion of binary system? This was called the quadrupole controversy. It was an active controversy. And what was known really, the only thing which was known for sure at the time was that the acceleration of a body, let's say the position Z1, body 1, as a contribution Newton's law 1 over r squared from the body 2. And the only relativistic correction was known at the level 1 over c squared, which means v squared over c squared, and g over c squared, which had been derived by Einstein, Infeld, and Hoffman in 1938. But beyond that, there were no actually good derivation, although there were some papers by a Japanese group, but they were self-contradictory and you could not put numbers. And I'm not going to discuss this. There was also an error in some integrals. But the effect is at the next order, you know, next leading order, where you need still an extra v over c compared to this, okay? And the reason why there was a debate is that when people had attempted to solve Einstein's equations going to this order, they used the near zone expansion, the post-Newtonian method of approximation, and this gave divergences. There were infrared divergences in the computation of local effects, and therefore you could not conclude, although people got saying, we see the radiation reaction, it was given by some infinite integral somewhere, so it was not satisfactory for sure. And also there was an incomplete treatment of nonlinear effects, and also there was also the fact that a neutron star is a very strongly self-gravitating object, so you cannot use perturbation theory on the pulsar itself, okay? Now, Jürgen Ehlers, in particular at the time, emphasized the need of having a derivation, which would be better than this. And around Jürgen Ehlers, Arnold Rosenblum was the first one saying, okay, as there is a problem with using the post-Newtonian expansion in 1 over c, let's use what was called at the time fast motion approximation, that is to say perturbative theory in powers of g, without assuming anything about a near zone, v over c or whatever, which is now called post-Minkowskian expansion, okay? And he said also, maybe if we do a scattering computation, it will be a clearer thing, okay? And he did a calculation. At the time, by the way, nobody believed this calculation was correct because also the order in G at which he was working was only the second order, while everybody knew the effect had to be at the third order. But I discussed with the editor of PRL at the time, and he said, okay, we are not convinced this is correct, but we are convinced that this will push people to do better calculations, so we published it in PRL. And in it, his result was that he found a result which differed from the quadrupole formula by a factor 2.3, okay? So at the time, there was a debate, and I remember I was also lucky to be there. In December 1978, in Munich, there was the 9th Texas Symposium, where Joe announced that he had measured already the variation of the orbital period of the binary pulsar, and it was in agreement with the naive formula deduced from the Einstein quadrupole formula at the 30% level, okay? And this was confirmed. So anyway, several groups of people said, let's work on this, let's clarify the thing. In particular, a group of people, and I was involved in this group, use post-Minkowskian methods, say, try to eliminate as far as possible any near zone assumption, expansion, and one could compute directly the equations of motion to the order g cubed over c5. They say, these are the full equations of motion. Here you have the 1 over r squared. Here you have v squared over c squared smaller. Here v4 over c4. And here v5 over c5 up to g cubed, which appear. There is a g squared in front and then a g cubed, okay? And let me not enter into the details, but we could prove that this part was conservative, that there was a Lagrangian, and then the 1/C5 was non-conservative, and then you could compute directly the observed effect. Let me also mention that at the time we found that there was an error in Landau-Lifshitz. I remember telling it to Lifshitz. He said, we never made errors, okay? But actually they did make an error. They corrected it to make another bad thing, but anyway, we learn things about gravity. But the main point I want to say is, because it is often forgotten, especially by now people from the LIGO-Virgo team don't emphasize so much that binary pulsars not only gave the first proof of the reality of gravitational radiation reaction effects, but that this proof is a direct, completely direct observational proof that gravity propagates at the velocity of light. Because remember Laplace, if you have something that propagates at the velocity of light, it will change immediately the force acting. And in GR, you need to take into account higher nonlinear effects, but you need to have retarded propagators at each level in your computation, okay? And it is because you have these equations that really come from solving Einstein equations in the system with retarded propagators up to the good order, that you finally compute directly what you observe, because you observe the period, you observe the change of the period, and this is directly linked to the fact that gravity propagates at the velocity of light. Actually, you know, in the computation, if you leave, like Laplace, the velocity of propagation of gravity not fixed, you call it CG instead of C, then from the data you get that CG is equal to C to now 10 minus 4, okay, and better than 10 minus 4, okay, so it's a direct proof. So you observe this, you observe directly this. Now, for instance, for the original Hulse-Taylor pulsar, where the orbital period, okay, so just to see, and we will see more from Michael, when you start looking at numbers from pulsar observers, you are struck by the accuracy with which they are measured. Like the orbital period at some reference time, you see, is a third of a day, but with 15 digits or 13 digits, okay? And then what happens is that this orbital period changes slowly over time, which means the time of passage at the periastron shifts over the years. So when Joe announced the result in '78, the shift was small, okay? But now you see over the years, you have like 65 seconds of shifts, okay? So it's a large effect because it accumulates over time. And numbers, so you observed a binary period change. You put in the timing formula that the binary period is not constant, but secularly changing. And then you fit for it from the data. Now I still remember why I had met Joe, and then before, and then I got an email from Joe saying, Thibault, it seems we have a problem because there is now a 2 sigma discrepancy between the observed change of the binary period and the one predicted by Einstein. And then we started racking our brains saying, okay, is GR wrong, or is there another reason why the observed change of orbital period is not what Einstein predicts? And then in a paper with Joe in '91, we found that there are several effects, but for this system, the dominant effect is the fact that the binary pulsar is somewhere in the galaxy and is accelerated by the gravitational field of the galaxy, okay? And therefore, between the pulsar and us, this distance varies in a nonlinear fashion, which means, if you want, the Doppler effect between the two of us is not constant. It's not a constant relative velocity, but a varying velocity. And therefore, when you take into account the acceleration by the galaxy, you should have contribution to P dot, because what you observed is a redshift period anyway. So if the redshift factor varies in time, you should subtract this, okay? So you need to subtract, and you compute this effect. You need to put the size of the galaxy, the mass of the galaxy, and then you subtract it. After you subtract it, you have this ratio. The intrinsic change of the orbital period is minus 2.398 10 minus 12, very small pure number. The GR effect is computed as minus 2.40, etc., 10 minus 12, and the ratio between the two, is 9983. Okay, so you have an agreement at the 2 10 minus 3, 2 parts in 1,000 agreement, and there is even better agreement from another pulsar. Let me also mention, Joe already mentioned this, the fact that you have a direct experimental proof also that you see binary system getting closer. From this, observationally, even if you don't know the theory of gravity, you can estimate when the system will get near, and therefore will collapse. And you know that in the last orbits, it will go very fast, as Freeman Dyson was the first one to point out. And therefore, this furnished the first clear proof that there existed in the universe objects that you could be detected as gravitational wave emitted, okay, from the last orbits. Now let me go back to the timing formula. So after this work, one knew the equations of motion of binary system, not only what was known before at the 1pn correction, v square over c square, but the 2pn and then the v5 over c5, okay? And as I said, what we observed is the arrival time on Earth of something emitted by a clock which moves in an orbit. So you need to know the orbit, the motion of this as a function of time, a local time, and then convert this to what you see on Earth. And therefore, you need to solve this equation explicitly. Actually, for most of the effects, because of the orders of magnitude, I said that v square over c square effects and v cube over c cube, finally, you are already at the microsecond level. You don't need to have the explicit solution of this part, except for some effects that Michael will talk about. And several people worked on this, but with Nathalie Derriel, we found a simple way of writing the solution. Okay, this is not a difficult theoretical exercise, but when you solve it like this, by brute force, you get very complicated formulas and you don't see anything. Why, if you massage a little bit thing, and you use some ideas, then you find that you can write the solution exactly in the form that Kepler was writing the solution of a two-body problem, with a Kepler equation relating the time along the orbit with an eccentric anomaly, with some eccentricity Et. Then the position R on the orbit is 1 minus E cosine of the same eccentric anomaly U, but with another eccentricity AR, and the polar angle on the orbit is given by the same formula as Kepler knew, with this arctangent, but there is another eccentricity, different from the first two, and then a factor in front, which is a Periason precession. So this is called quasi-Keplerian, and the advantage is that it allows you to think of what you can measure or not. And this gave, when you plug this in the derivation of the timing formula, so to summarize, the timing formula has to include many things. The proper time, let's say, of the pulsar for the nth term is related to the observed time on Earth. First, there is a factor D, which is the Doppler effect between the pulsar and us. That is not observable apart from when it varies. Then you have relativistic effects in the solar system, okay, by the sun here. And you have the dispersion. The signal has to pass through the interstellar plasma, and therefore radio waves are delayed by this propagation. And this goes like 1 over f squared. So if you measure things at different frequencies, you can take it away, this effect. And then you have really the observables coming from relativistic effect in the solar system that we, at the time, I put in order of Römer, Einstein, Shapiro, and aberration effect. I'm saying this, RESA, R-E-S-A, because this was the name of the dog of my brother at the time. So it was a way to remember this. And all these effects were given by simple formulas. And the advantage, so it was more complete than the one of Blanford and Tucholsky. And this allowed, then at the time I interacted with Joe. Joe visited IHES. We could work here and discover new tests of gravity with real data on magnetic tapes that he had brought from America. And we concocted a formalism that we call the parametrized post-Keplerian formalism. And the idea is the following. Mathematically, you have a formula which connects the observed time on Earth to an integer n and to some parameters. You have parameters which is the spin period of the pulsar, 59 milliseconds, the variation of this. But you have parameters that Kepler would have put, saying, okay, I have an elliptic orbit with some period, therefore I have an orbital period, I have an eccentricity, and I have the size of the orbit, projected size. So if only Newton was correct, everything would be contained in these parameters. But at the time, we found that not only general relativity, but more general theories, like scalar tensor theories of gravity, would include more terms, and they can be parameterized in a universal phenomenological fashion by some parameters. K represents the parameterization of the precession of the periastron precession, okay, the change of the periastron. Gamma, it was the gamma that appeared in some of the formulas. The Einstein effect is parameterized by gamma. Then you have the change of the orbital period. And the, yes, I should, because it will be important, so let me show, yes, the Shapiro delay, what we call the Shapiro delay. Okay, here. Yes, I should look at this, or it works here. Okay, this is the effect that the radio waves are propagating within the binary system, and they are slowed down by the fact that the companion has a certain mass and is seen at a certain angle. So this effect is a certain logarithm of something which depends on the orbit, and in front of the logarithm there is an amplitude which is in GR the mass of the companion. But you can say, I don't know, maybe it's a different theory of gravity, but maybe there is a Shapiro delay like this, and the mass which appears is not the mass of the companion, but something else. So I give a name to this parameter R, and this quantity S, which is sine of I call it the shape because it changes this thing. So you introduce a parametrization with parameters without saying that these parameters are given by a specific theory of gravity. And therefore, you can extract them from the data. So the conclusion is that in any given theory of gravity, if you have measured, and they are easy to measure, the Keplerian parameters, any parameter beyond this, post-Keplerian parameter, is a phenomenological way that you can, parameter that you can fit to the observational data. And if you measure a certain number of phenomenological parameters, it gives you, for instance, a periastron precession parameter, K, in any theory of gravity, will be a function of the two masses. In GR, this parameter is a function only of the sum of the two masses. The parameter gamma is a more complicated function of the two masses. So if you measure one parameter in the plane of the two masses, M1 and M2, that you don't know, because a priori you don't know the mass of the pulsar, you don't know the mass of its companion, it gives you one curve. Now, if you measure two such parameters, it gives two curves that intersect in general. For physicists, two curves always intersect. And they have to intersect because there should be values of M1 and M2 such that they correspond to the good value. And so at this stage, by using two phenomenological parameters, you have not a test of gravity, but you know the two masses. But if you measure a third parameter, then now this line, this curve, should pass through the same point as the other two. So you have a test of gravity. In GR, the formulas are given by this. And here, the conclusion is that, as I just said, if you measure three phenomenological parameterized post-Keplerian parameter, you have one test of the underlying theory of gravity. If you measure four parameters, you have two tests. If you measure five parameters, you have three tests, so n minus 2. And for instance, this figure illustrates, using a theoretical framework that I will describe very quickly that we built with Gilles Esposito-Fares, if you use actual data from the Hulse-Taylor initial binary pulsar, the measured value of the P dot is this straight line here, sorry, P dot is this curved line here. The other two is gamma and the periastron precession. Omega dot is here, and this is gamma, and this is P dot. In GR, the three curves exactly intersect, okay, modulo the error bar on this. But if you take the same phenomenological measured thing, but you interpret in a different theory of gravity, and a theory of gravity which actually makes no difference for any experiment you can do in the solar system, you find that the curves do not intersect, okay? So, so this is the idea of getting tests. Now results. This is the mass plane, the mass of the pulsar in solar mass. At the end, the values of the masses you get are of the order of 1.4. Okay, you find that the pulsar and its companion, two neutron stars, for this system have masses like 1.4 times the mass of the sun. So what I just said is from this pulsar, omega dot gives this line, gamma gives this line, and so from this intersection, you can measure the two masses, M1 and M2. And then if you compute what is the predicted intrinsic P dot as a function of the GR prediction from using the two other things, so you have only observable things, you get what I already mentioned, 9983, okay? Actually, you have more tests for, so this is the most accurate test, but you have 5 curves in the 1913+16 place, and actually there is even a 6th parameter, but which is not very accurate. It's difficult to get, but at least there is the Shapiro effects, as I said, is parameterized by 2 parameters, R and S. And Frère and Vex have said, but actually we can replace R and S by different functions of R and S, which are better measured, but easier to observe. And then this is what is plotted here, these 2 parameters. You see that you have this curve, and all those curves, finally, they overlap in one place. Okay, so from this, you have already 5 confirmation of generativity. Michael will talk at length in this beautiful system, the double pulsar. You see its name here, and it has A and B because you observed at the beginning, not always, we will hear about this, not only the main pulsar, but also its companion, also as a pulsar, okay? And therefore, you have a double line system. And then in this system, you have 9 observables, okay? You can observe 9 quantities, which gives 7 tests of gravity, okay? You see here you have all those lines, 9 lines. Some of them are thick lines, and they all intersect in one point in the middle, okay? Which is a fantastic confirmation of generativity. The most accurate test from this is the parameter S from the Shapiro time delay, where the ratio of the observed value to the GR predicted value using 2 other parameters, omega dot and gamma, is this beautiful thing, you know, 1.00009 plus or minus 2 10 minus 4. So it is the 10 minus 4 level accurate confirmation of strong field generativity. I will discuss now why, which is based on the propagation of electromagnetic waves in the system by the companion. And as Michael will show us more precisely, the curvature of space-time in the region where this radio wave are propagating is actually orders of magnitude larger than any other test of propagation of gravity, propagation of waves, photons in gravitational fields, okay? So it is very impressive, including the famous Event Horizon Telescope test, okay? Now, why are binary pulsars excellent tools for strong field test of gravity? There is first an intuitive argument. An intuitive argument is that if I fix a mass, like 1.4 solar mass, okay? From 1.4, I can make a neutron star. This neutron star is already very compact, okay? I can measure the compactness as the 2 times g, the mass of the neutron star divided by its radius, and this compactness is 0.45. If I crush it a little bit to make a black hole, the same mass, I will get a compactness, it will become a black hole, and the compactness will be 1. But you see that the difference between the compactness of a neutron star and a black hole is only a factor 2. So these objects are really strong field, okay? Nearly as strong field as black holes, although there are differences. And anyway, in order to show technically that indeed in binary pulsars you see strong field effects, the best way is to contrast general relativity with another theory of gravity, which have a different strong field behavior, and see that indeed you could have a difference that you would see in binary pulsar data. And now the most general tensor scalar theory of gravity with one scalar field would have a Lagrangian given by this thing, okay? You can put the action for the gravity and scalar sector in Einstein frame, which means where the kinetic terms are separated. And then you can say, can I have a potential also, which can be important in cosmology. But here I'm assuming that this potential is doing its job in cosmology, but has negligible effects in the solar system. And now you say that there is the Einstein metric which appears in the Einstein action, but the way matter couples to gravity is not simply by the metric g mu nu, but contains the g mu nu of the action and the scalar field. So you introduce a coupling function and saying, as a generalization of what comes out of string theory, the so-called, and which was actually first written down by Jordan and Firth in the 50s, and then Brents and Dickey further studied the simplest scalar theory of gravity. The simplest scalar theory of gravity is to say that the metric which couples to matter differs from this metric by an exponential factor, exponential phi, exponential alpha 0 phi, where alpha 0 is a certain number, okay, which is the Jordan, Firth, Brents, Dickey parameter. And if you say the log of this coupling function is not simply a linear function of phi, but a more general function, you can introduce a simple framework where you have not only one parameter, alpha 0, but also the one measuring the curvature of this function, and more terms, which in general, which do not play any role in the solar system. And if you take them away, it defines, just as a contrast to general relativity, a two-parameter class of theories of gravity that we introduced with Gilles Esposito-Fares. And what we had shown at the time is that in this simple theoretical framework, which has two parameters, it is enough that the first parameter, alpha 0, be extremely small, because this parameter alpha 0 is directly the linear coupling. It's the linear coupling. Alpha 0 is the coupling of the scalar field to a test particle. And if it is extremely small, you find that in the solar system, all the effects are extremely small, and therefore you cannot see any deviation in the solar system. If in the limit, if you take alpha 0 equals 0, you will see no effects. But what happens is, because of non-perturbative effects happening in the neutron star, there is a spontaneous scalarization, which means the scalar field suddenly appears from 0. There is a kind of phase transition, okay? And then when you have the strong field of a neutron star, and this parameter beta is still of order unity but negative, you find that suddenly a scalar field couples of the order, the coupling to a neutron star now becomes 0.6. Why, when you are in the solar system, the coupling can be 10 to the minus 100, whatever you want. Okay, so it's really a strong field effect, which just shows that this could exist, and therefore binary pulsar data tests something beyond solar system data. And this is the graph I had shown before for the Hulse Taylor pulsar. If you interpret the data in GR, everything is fine. And if you do, you take this theory for -6, which in the solar system is indistinguishable from GR, you find a difference of order unity, okay? So it is the proof that this is now, is from the recent paper of Paulo Freire and Norbert Wex, a summary of the constraints that you get both from solar system data and from several binary pulsars on the plane of the two theory parameters I mentioned, alpha 0, which is the coupling of the scalar field in the weak field limit, and this curvature parameter beta 0. The Jordan-Firth-Brans-Dicke, let's say, string theory-like theory would be the coupling function exponential alpha 0 phi, and which means beta 0 equals 0, so it would be along this line, okay? And then let's first look at this line. Okay, so this line is the simplest, let's say, one parameter theory of gravity. Solar system data says that the square of alpha 0 has to be smaller than 10⁻⁵. These are the so-called Cassini tests. So anyway, solar system tests say everything is okay if alpha 0 is, which is so it's the square root, this is the log, okay? And alpha 0 is the square root of 10⁻⁵. So it gives this minus 2.5 here. You are okay, but you see that one of the systems that Michael will describe, the triple system pulsar, is now giving a stronger limit on this parameter, on the Jordan-Firth-Brans-Dicke, than all the solar system. But if you go to the more interesting plane where you have also beta 0, you see that binary pulsars now are saying that there are many theories of gravity here, 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 that would be okay with the solar system data, but are excluded because of binary pulsar data, okay, because of strong field effects. Now, quickly, there are more, I mean, binary pulsars have given really many ways to test gravity. Other test is actually, is the effect we had pointed out in our paper with Remo, where we said, binary pulsars is a gyroscope, and therefore spin orbit effects, and in GI it's often called geodetic precession, that the spin should be like a parallelly propagated vector in space-time, and therefore should geodetically precess. You should be able to see this, and indeed it has been seen in the double binary pulsar, in PSR 1534, and in this thing. And for instance, one of the best tests of this from this pulsar here is the ratio of the observed spin orbit to the one predicted by GR when you measure sufficiently many parameters is 0.97. Okay, so it is a 3% test, you know, of this effect. There are better tests in the solar system, but here it is for strong field. That's why it's important that even the strongly self-gravitating object have this. Now, I already said that if you had when you have a scalar field or anything that emits dipole gravitational type radiation, you should see large effects. And in some of pulsars, which are on nearly circular orbits but with wide dwarf companion, you find that the dimensionless number orbital period change is measured at the level, you know, of 10⁻⁵. Okay, so it's a 10⁻⁴, you know. It's very impressive that the systems are so pure that you see a small effect at 10⁻⁴ level, and there is agreement between the GR effect and what you observe. So if you had any dipolar radiation, it would be totally excluded. It gives a strong limit, you know, on existence of any dipolar spin 1 component to gravity. Another type of effect that we pointed out a long time ago with Gerhard Schaefer is the analog, is the universality of free fall. The basic property of gravity that Galileo discovered and Newton emphasized, and then Einstein said it's very special, and then it was discovered later why it is really special, is the fact that all bodies fall in the gravitational field in the same way. GR is very special because not only test particles, you know, 1 kilogram of lead and 1 kilogram of copper fall in the same way, but if you take a strongly self-gravitating object, a neutron star, a black hole, they fall again in the same way. If you have a black hole of 1 kilogram, it falls like 1 kilogram of lead or whatever, in spite of all the strong self-gravity. Why in many theories of gravity, especially with scalar fields, this is not true, okay? So there are several binary pulsar systems where you can test that all bodies in the system fall in the same way with respect to other bodies, like in the galaxy. And at the time we said in particular, if you have systems, because, okay, we call that gravitational Stark effect. What is the Stark effect? The Stark effect says that if I have an atom and then I have, let's say I have the electron going around the proton, and I put this in an electric field, what happens is that the electric field acts differently on the electron and the proton. So you have an extra force acting on the particle going around, and this force polarizes the orbit. And this polarization is actually very strong because it is an unstable orbit if there is no periastron precession. So if you have an external, if you have a difference of acceleration in a binary system, gravitational acceleration, the orbit should be polarized, okay? And with some eccentricity EF that we could compute. The best test, so this was tested with many objects in the many binary pulsars, but the triple system that Michael will talk more about, using the results of Archibald and company, Balzan and company, gives the fact that the fractional difference in acceleration of two bodies in this system is smaller than 2 × 10⁻⁶. So you get really very accurate, you know, the better even accuracy than in the solar system, except that for test particle, we know that all bodies fall in the same way at 10⁻⁵. But here, these are not test bodies, but strongly self-gravitating bodies. Finally, another type of effect is if there was a cosmic variation of the constants, and for instance, of Newton's constant, of the gravitational interaction, this should have an effect on the orbital period. Also, it would give an additional contribution to the change of orbital period. And the limits from binary pulsars, from the most recent paper is from this, is that the fractional variation is smaller than 10⁻12 per year, which is, you know, 1% of a Hubble time. So there are some other tests which are better than this, but here we are at a level which is cosmologically interesting, okay? Michael will talk in much more detail about the astrophysical impact of the discovery of binary pulsar. Let me just very briefly say, the first one is for the first time it has been possible to measure the mass of neutron stars to very high accuracy. I just quote numbers, you know, for you to see. This is for the double binary pulsar, how many digits you can get on these masses. I already said that binary pulsars furnish the first proof that there existed in our universe systems that would, in hundreds of millions of years, emit sufficiently strong gravitational waves to be detected. And therefore, it means if you go further in the universe, there will be systems that, binary pulsars that are collapsing now, are in the last orbit. Let me mention in passing that this thing was first conceived by Freeman Dyson in 1963, at a time where nobody believed in neutron stars, before the discovery of the first pulsar, you know, but Freeman had the vision that this was interesting. And, but we will hear more from, I think, from Michael. The fact also, especially after the discovery of millisecond pulsars, but even before, Steve Detweiler was the first one to say that as pulsars, they don't need for this to be binary pulsars, but the accurate with stable periods are as accurate clocks as atomic clocks, okay? But they are somewhere in the galaxy. If there is a low frequency gravitational wave passing through the galaxy, it will be like if you are in a medium where the index of refraction changes and you expect that the pulsar and the Earth will move around because of this gravitational wave, and therefore the timing data will reflect the existence of a gravitational wave passing by, okay? And this has been realized over the years with the construction of several pulsar timing arrays, which means collection of good pulsars. And recently they have announced that they have detected, indeed, very low frequency, or it seems quasi-certain, they have discovered it's a different way of detecting gravitational waves. They could have detected gravitational waves before LIGO, and apparently they detected it after, okay? But it's very important. Just Now, the conclusions. The conclusion is evident. The discovery of the Hulse-Taylor pulsar has given us a cornucopia of important scientific benefits. Let me just highlight again, from the theoretical point of view, the most important thing. It's the first direct observational proof that gravity propagates at the velocity of light, is mainly quadrupolar, and that its nonlinear behavior is described by GR in detail. And remember that we will get this from the double binary pulsar, this impressive argument, you know, at the 10⁻⁴ level here. Then there are, is it this? Okay. The first precision test of the strong field regime of relativistic gravity, because this test mixes, in a sense, strong field effects in the neutron star and radiative effects. But there are other tests, like the S measurement in the double binary pulsar and in the Hulse-Taylor pulsar, where they are totally, they don't care about propagation effects and radiation reaction effects, but they test that the strong field behavior in gravity is the one of GR at the level, for instance, Michael will describe this. This is 2⁻⁴ thing. From the theoretical point of view, it has obliged, the discovery of the binary pulsar has pushed theorists to say, okay, we have to think, because, you know, Einstein in the early days, okay, Einstein wrote a first paper saying, let me solve Einstein equation. He would not say this, but let me solve the equation published in November 1915 by an expansion in amplitude, like I have h mu nu, g mu nu equal eta mu nu plus h mu nu, first order, okay. Then when he discussed immediately actually solar system, he said, but I need to take into account V over C effects, the fact that the velocities are small. And Einstein and Johannes Drost introduced what we call now post-Newtonian expansion. But the post-Newtonian expansion says also that everything is slow. And therefore, when you solve the D'Alembert equation, you know, Laplace minus 1 over c squared d squared by dt squared, you say 1 over c squared d squared by dt squared is small. You put it on the right-hand side and you solve it this way. But this is valid only in the near zone. And this was creating, at the time of the discovery of the pulsar, many problems. That's why people emphasize, no, we have to go to post-Minkowskian gravity, where you are very careful about near zone effects, you know, radiation type gravitons and things. And this is still ongoing. Now there is a new effort of post-Minkowskian gravity with very interesting results. In particular, my new colleague here at IHES, Julio Parra-Martinez, who I hope is on Zoom, has provided very important results along this direction. Now, at the end, binary pulsar tests are so numerous and so accurate that they have excluded many theories of gravity, and the ones that are not excluded, you know, are constrained to special regions of parameter space. So really, we have learned a lot. We have really learned that GR is confirmed in the strong field regime, and apparently nothing else can exist in the strong field regime. And the triple system have opened new windows, and we will hear from Michael that maybe one has already discovered a very interesting new type of binary system where the companion is a black hole. Okay, thank you for your attention.